So welcome everyone. It is our great pleasure today to welcome Professor Anne-Christine Hladky Hennion. She was awarded the Diplôme d'ingénieur of the Institut Supérieur de l'électronique et du numérique in 1987, and then a PhD degree in material science from University of Science and Technology of Lille in 1990. She has done important work on acoustic metamaterials, and today she's going to present her latest work on tunability of electrically controlled piezoelectric phononic crystals. And Christine, the stage is yours.
Okay, thank you. Hello, everybody, ladies and gentlemen. So first, I would like to thank the organizer, Bogdan and Sebastian, for inviting me to give a talk. Yeah, and so the title is Tunability of Electrically Controlled Piezoelectric Phononic Crystals. And first, I would like to thank my colleague and to associate my colleagues. So Ricardo Alcorta-Galvan, PhD student, Charles Croen and Bertrand Dubus, they are CNRS researcher in Lille. And I would like also to associate my colleagues from Thales Research Technology, Mai Fanti, she is retired now, Brigitte Loiseau, Étienne Eustache, and Mathieu Bertrand from Thales. So, as you know, phononic crystals are periodic structures exhibiting band gaps, and due to the lattice that can be rectangular, triangular, and so on, due to the materials and due to the shape of the inclusion, so you can have a band gap. It means that the waves are evanescent, and the name of these gaps are Bragg band gap, and they are due to the periodicity. So if you want to know the behavior of the phononic crystal, then draw the dispersion curve, like in this case, so triangular lattice of steel cylinders in water. And so you draw the frequency versus the wave number for different propagation directions. And then from these curves, you can identify the passband, the stop band. The stop bands, it can be a stop band in a given direction, propagation direction, like in the green case, or it can be a stop band for any propagation direction, like in the pink color here. So it is an absolute band gap. So here, rapidly, the first experimental demonstration of the Bragg band gap. So it is with a sculpture from the artist Eusebio Sempere in Madrid. So you have steel rods, 2.9 centimeter in diameter, square lattice, side 10 centimeter, and you have an attenuation around 2 kilohertz. And if you draw the dispersion curve here, you see that you have a band gap in a particular propagation direction. So the phenomena of filtering is the main application, the first application of band gap, but you can imagine more complex functions using the band gap. And this is a nice illustration made by Abdelkrim Khelif from Fento in Besançon. So you have steel cylinders in water, a square lattice. So you have a stop band between 185 kilohertz and 325 kilohertz. And if you remove one line of cylinders, then you create a passband inside the previous stop band. And then if you remove more cylinders, like in this case, only one, or periodically you remove cylinders, like in the case of the figure here, then you can create a stop band inside the previous passband that was inside the previous stop band. So you can have fun by imagining more complex filtering functions. In the previous cases, the matrix was fluid, it was air, it was water. And in that case, you have only one branch starting from the origin. In the case of solid matrix, like in this one, square lattice of steel cylinders in epoxy, then starting from zero, you have three branches. one for the longitudinal wave and two for the pseudo-transverse waves. But it is the same. You draw the dispersion curve and then you try to identify band gaps in a specific propagation direction or for all the directions. So in the first case, it's the green color, then the pink color. For the previous case, the problem is that if you want a good efficiency, the thickness has to be large because you have to take into account several periods. So it can be very heavy. So it is rather high frequency. So if you want to have a band gap at lower frequency, so in that case, you can use resonances. And in that case, we call that hybridation band gap. And this is the case for the famous paper from Pingsheng with lead spheres, 1 centimeter in diameter with a rubber layer all in epoxy. And you have at low frequency a gap, hybridation band gap. And so you can have attenuation even for small thickness. Depending on the frequency range of interest, so you can imagine very, very different applications. At very low frequency, you have seismic applications, and you can have application for underwater acoustics, for sonar, for stills or discretion. In the audible range, frequency range, you can have sonic screens like this one with bamboos in Le Mans, and at higher frequency you have also some applications for ultrasound imaging, auto mechanics, and so on. Here it is the plan of my talk. So phononic, as I said, phononic crystals can modify the propagation of waves, and the modification is related to the geometrical parameter and the materials. But as soon as the phononic crystal is built, then the bandwidths are fixed. Here, we would like to tune the band gaps. And the way to tune the band gap is to use piezoelectric materials. In piezoelectric materials, you have a coupling between the displacement and the electric field. It means that when you apply a displacement on the piezoelectric material, then you see an electric field, and reversely, if you put an electric field on a piezoelectric materials, there is a strain. So here we will try to confer tunability to the band gaps by changing the electrical connection. And I will present you two examples. First, the rods, and very new results on SAW components. In my lab, we are working on phononic crystals and periodic structures for about 30 years. So the idea is to develop a general model to get the dispersion curve, and the mesh based on the finite element method using the Attila code. We mesh only one unit cell. We apply the phase relations on the surface, and then for given k value, wave number value, so you can do a model analysis and you get the eigenfrequency, and then by changing the wave number, you draw the dispersion curves. So first, the example is about the rods. Here you see you have a stack of piezoelectric rods. They are all pulled along their thickness, and between all the rods you have some electrodes. And you will change the connection on the electrodes of the rods. So we imagine that harmonic plane wave is propagating with longitudinal polarization, and we have developed a one-dimensional analytical model. So first we have written the equations of piezoelectricity, and we have written the continuity and the Bloch-Floquet equation for the stress and for the displacement. And then we have solved the equations, and we have got the dispersion relation that is here. In this dispersion relation, you have an additional term, alpha, which is related to the capacitance that you put at the bond at the extremity of the rod. If all the electrodes are in open circuit, so in that case alpha is equal to 0, and you have exactly the dispersion relation for an homogeneous material. As soon as you put an external capacitance, of if it is short-circuited, then you see, due to the alpha term, you will change the dispersion relation. In the large wavelength limit, you can have also, you can find the effective velocity like this one. So this is the result for the analytical model. So in the first case, on the left, all the electrodes are in open circuit. So in that case, you have the propagation in the material. It is like an homogeneous material. Then you have a capacitance connected to each rod, and in that case, you see there is a small band gap that appears. And then, if all the electrodes are in a short circuit, so in that case, you see a band gap at the boundary of the Brillouin zone. The lower frequency of the band gap is the resonance frequency of the rod, and the upper frequency of the band gap is the anti-resonance frequency. It means that the width of the band gap is related to the electromechanical coupling factor of the material. Now the question is, why is there a gap? So in fact, in these cases, you have some changing, some charges appears on the electrodes. So electrical displacement is constant in each rod, but is discontinuous from one rod to the next. And this discontinuity implies a band gap. Its name is the electric charge band gap, Bragg band gap. So here you have the full line, it is the analytical model, the relation that was in the previous slide, and the dots is the finite element results using Attila code, and a patent has been filed for this, with this concept. Then here are the experimental evidence of the electrical charge Bragg band gap. So you see we have here a stack with 14 PZ29 rods, 10 millimeters long, 5 millimeter radius. In the first case, so we apply an excitation on the left, and we see the transmission on the right. First, all the electrodes are in open circuit. In that case, the propagation is like in an homogeneous material, and it is the blue curve here, and the transmission is quite constant for all the frequency range. Then we apply the electrodes are in short circuit, and in that case, we see a drop in the transmission that corresponds to the electric charge Bragg band gap. Here you have the dispersion curve. So here it is the evidence, experimental evidence of the electric charge Bragg band gap. Then we can have fun. So if you do a proper choice of the capacitance, like in this one, so you can have a fixed upper higher value of the band gap, and you can change the lower value of the band gap. By another proper choice of the capacitance, C2, you can have a fixed lower frequency of the band gap and a variable frequency of the upper value of the band gap. And then we can have fun by mixing these two solutions. And so we can have a fixed central frequency and variable bandwidth, or we can have a fixed bandwidth, but a variable central frequency. Okay, now the questions for the next is, what are the specific effects when the electrodes connections are time dependent? So in that case, you imagine again the stack of rods, and we will have a switch on each electrode, and they will be connected simultaneously. So the electrical connections are simultaneously connected to ground with a velocity V that can be positive from left to right or negative from right to left. In that case, it is a modulated phononic crystal. So one-dimensional model has been developed based on the FDTD. We have PML at each extremity, and the source is on the left, and we see what happens on the right. All the model is presented in a paper, APL paper, in 5 years ago. And here you have on the left the dispersion curve with static case, so no velocity for the electrodes change, and so you have band gap. And as soon as you change the connection with a given velocity, negative or positive, you see the main change is that the dispersion curve is not anymore symmetric. It means that for positive k value or negative k value, wave number value, you don't have the same band gap. And so in that case, it is the evidence of non-reciprocity. So you will not have the same propagation from left to right and right to left. Experiments are in progress. And they have been done in the frame of Sarah Tessier's PhD thesis, and it will be presented for the first time next month at the ASA meeting in Denver. Now, the second part of my talk is about tunable SAW, surface acoustic wave. This table shows the United States frequency allocations. So you have many colors, many frequencies. If you do a zoom like this one, you have here the zoom on the right, you see that you have specific frequency bandwidth. For instance, here it is between 2 gigahertz and 220 gigahertz and 225 gigahertz, and all this band are allocated for specific applications. It can be for mobile phone, it can be for space research, and so on. About 10 or more, 15 years ago, with your smartphone, in your smartphone, you had about 5 filters. The filters are based on SAW. But your smartphone, you could use it in the States, but not in Europe. You could use it in Europe, but not in Japan, and so on. Today, with your smartphone, you can use it in the States, in Europe, or in Japan. It's with the same smartphone. Why? That because inside you have a lot of filters. That on each filter, and the filters are dedicated to specific frequency band. A lot of filters in your smartphone, so it takes place, it has a cost, and it can be a problem if you have one or several filters that are not working well, if you have defects. So the goal now is to have less filters, but tunable filters. And the base is the SAW, surface acoustic waves. So surface acoustic waves, you consider a semi-infinite piezoelectric substrate. You put electrodes on the top at the surface, periodic electrodes, and you have interdigitated electrodes. So it means that on one part you have +1 volt, on the other one you have -1 volt. And then when you apply this voltage, there is a deformation at the surface of the piezoelectric surface, and then a wave will be propagated on the substrate. Okay, so now this is SAW. For RF components, a basic element is a resonator. A resonator is one transducer at the center, so interdigitated electrodes like I described just before, and you have 2 Bragg mirrors on both sides, on the right, on the left, on the left and on the right. Then, based on a resonator, you can have filters. So filters it is two transducers that are coupled that, for instance, if you have a cavity, or you imagine also several resonators that are placed in order to build a ladder. For a filter, you have here the response, what the expected response. So you have frequency band, and in this frequency band, you want to have a good level, and this is the expected response you want for a filter. So now the question is, can we use the Bragg mirror to have a tunable resonator? So Bragg mirror is a very simple device. It's only a periodic arrangement of electrodes on the surface of the piezoelectric substrate. So you have here only one electrode of the mirror. So you have here the lithium niobate substrate, and here you have PML. First, on the electrode, you will put a short circuit. You will get a band gap, and second, the same but open circuit on the surface, and you have another band gap. And this is the shift of the band gap that will help us to have tunable resonator. Here you have the dispersion curve of the device I just present you. So in that case, the goal is to have a filter. The goal is to have a filter around 400 megahertz. So with the device here, so the period will be 4.87 micrometers, and A over P is 0.455. A is the thickness of the electrodes, P is the period. And as you can see, depending on the electrical connections that you put on the electrode on the top of the surface, then you have different band gap, short circuit here, and open circuit. And so you have two different band gap depending on the electrical connections. So this is a very interesting result. And by changing the A over P ratio, you see that you can tune the band gap, ground, short circuit, or open circuit band gap. And here for the next devices, we have put A over P equal 0.455. Why? It is because in that case, it is just at the middle here, you have two band gaps for ground and open circuit conditions. Okay, if A over P is too low or too large, you have only a band gap for ground or a band gap for open circuit. But in that case, at the middle, you have the two band gaps. So now you imagine a resonator. So a transducer in the middle and the two Bragg mirror. For each Bragg mirror has, in that case, 72 electrodes. In the middle, it is a transducer, very classical transducer with interdigitated electrodes. And in this diagram on the right is very important because it is the S11 coefficient. It means the yellow color corresponds to the resonance of the resonator. And knock is the number of electrodes of the mirror in open circuit. So if knock is equal to 0, in that case, all the the electrodes in the mirror are short circuit. If n knock is equal to 10, then the first 10 electrodes are in open circuit, and then the 62 next are in short circuit, and so on. So knock is varying from 0 to 72. And you see the different colors here. And it's very interesting because, for instance, on the A point, so as you change a little bit the electrical connections of the Bragg mirror, then you have a continuous shift of the resonance frequency. But you can imagine to have a larger jump for instance, from 0 to 50. In that case, you have clearly a jump of the resonance frequency. Now, thanks to the previous diagram, we have done fabrication and test on this device. So it is here a comparison, measurement and simulation, and we see 3% of tunability. So here on the left, you have the pictures of the devices. The first is short circuit. Then the second one, you have 10 electrodes in open circuit, then 30 electrodes, 50 electrodes, and then all are in open circuit. It means that 72 electrodes are in open circuit. And clearly on this device, on this picture, you see the variation of the resonance frequency. It means that you can tune the response of the resonator by a change of the electrical connection. So this will be published very soon in APL. It has been accepted last week. Okay, but in the previous device, the problem is that the connection will be very complex. So you imagine you have a great number of electrodes that have to be shifted from short circuit to open circuit. So you imagine, for instance, you change from 0 to 10 electrodes, so you need at least 10 switch for the shift to shift the components. So it's too much. Okay, so the connections will be very, very complex. So we have to imagine how to simplify the connections instead of using 10, 30, 50 switches, but we have to imagine to have very low number of switches. And to have the solution to simplify the connection, we have noticed this that is very, very important. First, here on the left, you imagine we have a unit cell with two periods. First, the electrodes on the top are both in short circuit. Okay, we get the band gap like in short circuit case, like previously, no problem. On the right part, you imagine again a unit cell with two electrodes, but both electrodes are in open circuit. In that case, you have also the band gaps for the open circuit case, like previously, it's okay. But what is interesting, it's the case in the middle. In the middle, you have a unit cell with two electrodes, but the first one is ground and the second one is open circuit. And in that case, when you draw the dispersion curve, you see that the band gap is the same as the open circuit band gap. And this result is very important because it will help us for the connections, because now we can use interdigitated electrodes for the mirror, the band gap will be preserved. So instead of having 10 or 30 or 50 electrodes with different connection, in fact, you have only two. One is grounded and the other one is connected. Okay, so simplification of the connection. We have done some numerical analysis, and here you have the experimental results, and we see a shift of 2.25% in the resonance frequency on short circuit, open circuit. This is a very interesting result because with only one switch, we can have two frequencies for the resonator. So now the resonator, having a switchable resonator or tunable resonator, it's good. But now what happens for a filter? So now we can imagine to introduce this switchable resonator inside a filter. So here we are doing the design of a filter by geometric dilation of the switchable resonator. Here we have done the choice to build a ladder filter. So you have here one cell here with a parallel and series resonator. And the idea, but it's a well-known idea is to use the series resonance must coincide with the parallel anti-resonance. And in that case, you build one cell of the ladder filter, and then if you have a more strong response of the ladder filter, then instead of using one cell, you use 2 cells, 3 cells, 4 cells, and so on. Okay, this is the end of my talk. So as a conclusion, so here I spend more time for the SAW component because it's a very new result, and we believe that it is important. So the main conclusion is that we have done a proof of concept of the use of the electrical Bragg band gap for the tunability of SAW components. For the resonator, we have a continuous shift or a jump of the resonance frequency. And we have done an experimental demonstration with a connection of a pack of electrodes. So we have a simplification of the connection. So it's a good thing. And now what's the next? So for the ladder filter, we have today numerical results. And now experiments are under progress with Thales research technology in Palaiseau. All what has been presented, we are using finite element codes. It can be Attila, it can be COMSOL, but as soon as we want to have a faster design of the resonator of the filter, we need optimization tools, and finite element codes like Attila and COMSOL. It's not easy to use this finite element codes, and so the idea is to use more simplified models like mixed matrix models to design the resonators and filters. Here I have presented you at the end a ladder filter. But we can imagine to use to apply this concept to other types of SAW components. It can be cavity filters and so on. We have also to improve the electronic control and the packaging. And what I have presented, it was with lithium niobate, but we can also apply this concept to other piezoelectric material like POI, other substrate, and so on. And now, acknowledgements. So first, I would like to thank Thales Research Technology, Palaiseau near Paris, and Région Hauts-de-France. They have supported our work with 3 PhD grants. So Sébastien Degrave, Clément Vasseur, and now Ricardo Alcorta Galvan. We have got support from the ANR and the defense, also the AID, and we have still a project for Formosa in progress. And finally, we have 2 patents for this topic. The first one on the road, it's the first patent, and the second one for the surface acoustic wave. It is the second patent about 2 years ago. Okay, thank you.
Thank you very much, Anne-Christine, for this really nice talk. So I think we have many questions from the audience. I would like to encourage people to come forward with their questions.